Hello everyone, welcome to the TheGeoecolologist. I am Dr. Krishnanand and you have been watching my videos on geography's various topics on my channel. So if you are new to this channel, do like and subscribe our channel, and we are going to do this entire series for optional geography, for UPSC exams and various other topics of geography, as well as you can check in the playlist. So in today's session on climatology, we are going to learn about a very interesting phenomena, that is adiabatic phenomena. So what is this adiabatic lapse rate all about? In the previous session, we have already learned about what is lapse rate. So what is this adiabatic process all about? Let's go ahead and find out. But before we go ahead, don't forget to subscribe to our channel and share the videos with others as well. So now, after we have learned this lapse rate and its various factors and processes associated to it and its various types, in this session let's understand what is this adiabatic lapse rate. Now I remember that this is one topic where many people are very confused. They don't have clarity that what is this adiabatic all about. What does this word basically mean? So let's start with this basic idea of this word itself, coming from the ancient Greece, that is adiabatos. So what does adiabatos mean? It basically means impossible. It means that something is not allowing things to pass from inside to outside. So it is inside only. It is not possible outside, and outside cannot come inside. So that is where it is like an opaque situation, right? Nothing can pass. So if it is an impossible situation, that is not through possible. So if it is not possible to pass through, in that situation, what is the situation of lapse rate? That is what is adiabatic lapse rate. So remember, the lapse rate, when related to this adiabatos or adiabatic situation, in totality it is known as adiabatic lapse rate. Now let's elaborate and understand in simplistic manner that what is this adiabatic lapse rate and how it is related to the atmospheric stability and instability as well. So the first important thing to understand is that adiabatic process in thermodynamics, remember thermodynamics is an important branch of science where this temperature and pressure and all these changes that we study, right? So adiabatic in thermodynamics basically is a change in volume without change in heat. So this statement, if you remember, it's a very simple statement that what is the change and what does not change. So two factors I'm telling you. One is something that is changing and one is something that is not changing. So those are important here to mark. So what changes here is the volume change, but what does not change is this change of heat. It remains constant. So one is constant, one is changing. So now remember, this is a constant variable phenomena that we should understand. That's where this adiabatic process is important. Remember, something has to be impossible, something has to be constant, and inside that something there is a variation which is going on. So this is where adiabatic process in thermodynamics, the word itself is therm, that is heat. So dynamics of heat we are going to study in terms of the lapse rate, that is change in temperature with altitude, what happens. So adiabatic lapse rate is the rate of fall in temperature, that is basic lapse rate definition itself, of a rising or a falling air parcel. Now remember, in normal lapse rate what we studied, it was a non-rising air in a normal situation. But here, what are we looking at? It is talking about a rising or a falling air parcel. So that is what is the difference. The first difference you identify is this: a rising or a falling air parcel has to be there when we are studying it, the adiabatic process, that is about adiabatic changes. So adiabatic or adiabatically, heat does not enter or leave the system. So the entire crux of the matter, always remember that one thing which is constant here is that in a system, if we say this is a system, what is impossible? The H factor, the heat factor. So heat is not going to leave or heat is not going to enter in this system whenever we say this adiabatic process. It means one system where this heat transfer does not happen. Right? So that is important. So where is the change all about? The change is in this volume thing. So all temperature changes are only internal to the system. So nothing comes from outside, nothing goes out from inside. So everything is internalized in that rising or falling air parcel. So remember, if this is a rising air parcel, so a fixed mass of air, a fixed particular boundary if we can make it, but a boundary is not possible to make in that way. But if we can understand that this is a fixed parcel, in that fixed parcel which is maybe rising or falling, what is happening? because now nothing is coming from inside in terms of heat and nothing is going outside in terms of heat. So everything is happening internally. So how do we learn about it? For learning this adiabatic process, part of the thermodynamics that we say, it is important to actually learn something which is the basis for this understanding of the adiabatic process. So this is called gas laws. Remember in the lapse rate as well, we talked about pressure and temperature relationship. So gas laws are something that is important part to learn in terms of thermodynamics, which has a role to play in climatology. So if you want to learn climatology well, you must understand these gas laws and specifically this process where there is dynamism involved. So it is not a normal case, it is a rising and falling case of an air parcel. So gas laws are important to learn here. So let's understand what are these gas laws and what do they have to say about this thermodynamics in adiabatic process. So the gas laws are basically talking about a relationship of three brothers, as I said. Three brothers are PVT, okay, and they have different combinations and permutations in their relationships. So pressure is the one brother, second is the volume, and temperature is the third brother. Now ladies and girls will be offended that why are you saying brothers, why not us? So you consider yourself as three sisters as well. So pressure is the first sister, volume is the second sister, and temperature is the third sister, as you may consider it in your own context. So now this PVT is all about what we need to learn in terms of gas laws and see how this pressure, volume, temperature have relationships in particular cases. So first person who's a renowned scholar is Boyle. So Robert Boyle, you look at this particular time period, it is 17th century. The science was actually developing at that particular time. So he gave this particular law on the basis of his experiments, and it is called PV law, that is pressure volume law. So in this, what are we considering? Which two brothers or sisters? Only pressure and volume. It means the third one is left out. But it's not left out. Remember, the third one is what? Constant. So remember how to learn this. The story of these three brothers or three sisters is whichever two are considered and third is left out, it is actually considered as constant. So what is the relationship here? The V part, the volume is inversely proportional to the pressure. So it means if volume increases, pressure decreases. If pressure increases, volume decreases. So this kind of relationship is what is given by Boyle's law. So the volume of a given amount of gas held at a constant temperature. So here is the third brother or sister, as I was saying, it is left out, but it is constant. So it is considered to be of same condition. So the variation is where? Variation is here that it is inversely with the applied pressure when the temperature and mass are constant. So here also what we say is a given parcel of air when we say adiabatic lapse rate. So the mass is constant. So how is it related? Remember, the volume changes with pressure changes. So if pressure changes positively, it means if pressure is supposedly rising or falling, accordingly the volume will also rise and fall. So this is first gas law, that is important. Come to the second one, that is called Charles' law. Remember now in the next century, that is 18th century. Now here is the story of next time the two brothers again or two sisters, that is TV. So here TV is being talked about, but what is left out here is the peak factor. So the left out is constant, as I say. So remember, it is easier to understand if you are knowing about what is being considered and what is left out of the three. So when something is left out, it means it is constant. That is the way to remember. So what is the statement of this particular law? So this law states that the volume of a given amount of gas, again the volume is important here, held at what? The constant here is pressure. Remember that? So pressure is constant, and what is the situation? It is directly proportional to the temperature, right? So the situation is V is directly proportional to T. So Charles' law says that when pressure is constant, then V is directly proportional to T. So if V increases, T increases. If V goes down, T goes down. So this is the next law that we study in gas laws. Now go to the next one. So the next one is about the PT factor. So what is left out is the V factor, right? So in condition where volume is constant, so what is the relationship between pressure and temperature? They are directly proportional here. And remember again, in 18th century, it is called Gay-Lussac's law, the name of the scientist. So in this particular law, what is stated is that pressure of a given amount of gas held at a constant volume is directly proportional to the Kelvin temperature. So here pressure is directly proportional to temperature, which we are talking about in adiabatic lapse rate as well. So when we see these three different gas laws, there is also another important law, that is to understand here the combined gas laws. So what is the combination of these three? What we see is that volume is directly proportional to temperature and inversely proportional to pressure. So if we combine these gas laws, we get this particular equation. So volume relationship with temperature is direct and volume relationship with pressure is inverse. So this is important, which leads to the understanding or better understanding of what happens in our atmosphere in terms of the adiabatic process, where there is a constancy, as we see, right? The system is having a constant heat which is neither going out and nor extra heat is coming inside the system, right? So there is this fixed parcel of air in which every change is happening internally. So that is where in this ideal condition, these gas laws play a particular key role to give us a better understanding. So that is where this ideal gas law becomes important. So assuming an ideal situation, that gas being measured in an ideal gas situation, right? So atmosphere is made up of gases. So we are talking about atmosphere here. So what happens? Over a wide range of temperature, pressure and volume, real gases deviate slightly from the ideal. Remember, there are various gases and ideal situation is the best situation, right? It is kind of 100% thing. So what is the deviation? Remember, the deviations is all about this particular PV and T relationship. So the ideal gas law is PV is equal to this N and RT. So what is this N here? N is the number of moles and R is a constant which is here to apply to this particular equation to remove this proportional symbol, as we say. So what we see here is that R is a constant, and this is also known as universal gas constant, and its value is this value that you see here. So now what happens? The adiabatic change refers to the change in temperature with pressure. Now remember, what is here? Change in temperature with pressure. So what is here? T and P relationship we are observing. So what happens when we go in altitude above atmosphere? There is a change in pressure. Accordingly, there is a change in temperature as well. So there is variation of a given parcel of air. So that is what we study here. On a descent, now here the descent is what? It is coming down, that is falling parcel of air. Remember, through atmosphere what happens? The lower layers are compressed under atmospheric pressure. So here is the P factor for you. So P factor is actually compressing the lower levels air, right? As a result, what happens? If P is actually compressing, the temperature increases. So this is the first case that we see. Remember the gas laws, P and T relationship. Now, on ascent, what happens? If we go up, then what happens? The air expands as pressure decreases with height, right? So air expands, and what will happen automatically? There is a expansion that reduces this temperature, and this aids the condensation of water vapor. Remember the cloud formation and water vapor. So this is important here. So condensation of water vapor releases heat. Now remember, this is important point here. And in later lectures when we study cyclone, we will study this again. These terms will come again. So remember this basic here right now. So the latent heat, the word is latent. Latent basically means hidden. So what is hidden here? The heat is hidden. Where? In the water vapor. Remember, in the lectures earlier to this, in insulation, we have learned what happens, that during the evaporation, heat is actually accumulated and heat is absorbed by water when it goes into the other form. So heat is trapped, and that heat which is part of the molecules, the intermolecular spaces, that is called latent heat, the hidden heat. So what happens here? In condensation, there is this release of latent heat of condensation in this process. So remember, that is important. And this latent heat, the hidden heat of condensation, is a major driving force behind tropical cyclones and convectional rains. So when we study types of rainfall and also these cyclones, that is specifically tropical cyclones, again this latent heat of condensation will be discussed. But for here, understand these two cases. What happens when we go up? What happens when we come down? In these cases, how does this pressure and temperature behave? And that is what we study under adiabatic changes. That is, in a given parcel of air, what is the relationship of temperature and pressure? So remember, that is important to understand here. So now this adiabatic lapse rate are usually defined as dry as well as wet. So remember, a situation where water vapor is not there, a situation where immense water vapor is there, right? So first thing that you need to know is what will be the case in dry and wet. Remember, if it is dry, so dry adiabatic lapse rate, that is also called DALR. So remember, this DALR is dry adiabatic lapse rate. So wherever it is written in short form, remember about adiabatic process is the key here. So it is the rate of fall in temperature with altitude for a parcel of dry or unsaturated air. So that is important. It is unsaturated. It means the saturation level is not reached 100%. It means it has capacity to absorb more moisture. It is a dry air parcel, right? So in that case, what is the humidity factor if we see? Unsaturated air has less than 100%. It has not reached 100% relative humidity level. So this dry adiabatic lapse rate equals for Earth's atmosphere, that is about 8 degrees C per kilometer. So this lapse rate, remember, dry adiabatic lapse rate is 8 degrees C per kilometer. It is higher in value, right? So dry adiabatic lapse rate is mainly associated with the stable conditions. The stability is associated when the situation is dry. But at the same time, remember, when there is this latent heat in the wet condition, what will happen? Now you can guess. Instability will happen. Because of what reason? That hidden heat of condensation, that is latent heat of condensation. So let's understand the wet situation here. So the moist adiabatic lapse rate, what we say, the rate varies considerably because the amount of water vapor in the air is high, right? And if the water vapor is high, so greater amount of water vapor, smaller is the adiabatic lapse rate. That is the key here. But why is it so? Again, come to this latent heat of condensation, as you know, because the condensation process keeps on adding more latent heat, and that's where this is instability that we say. So on an average, it is taken to be 4 degrees C per kilometer. So now when you go ahead in this situation, it is just 4 degrees C where water vapor is more. But in that dry situation, it was 8 degrees C cooler when we go in height. So dry situation is a normal situation where it is stable situation, but wet situation, you have more heat, which is part of the internal heat of the system. Nothing is coming from outside, but internally, due to this condensation, latent heat of condensation, there is this temperature here, right? So what happens? The temperature is higher in this case. That's why it does not decrease rapidly. It decreases rather at a lower rate in comparison to the dry one. So when we say dry adiabatic lapse rate and wet adiabatic lapse rate, remember to factor this, the latent heat of condensation due to more moisture condition, right? So that is the difference. So that is associated with this unstable condition, right? Because it has more moisture, and moisture has this latent heat. And remember, this is going to come again and again in the entire climatology lecture and also in some parts in oceanography when we talk about this process of evaporation and condensation and formation of tropical cyclone. So this is the key factor here. So that's why it is important to understand this dry adiabatic lapse rate as well and wet or moist adiabatic lapse rate as well. So now I hope that after learning the lapse rate and adiabatic lapse rate, you must understand how this entire vertical temperature distribution functions. But apart from these factors, we are going to learn in the sessions to come about inversion of temperature. That is the reverse of this phenomena, that is lapse rate. So stay tuned, stay safe, and all my best wishes.